The medium-range jet. The example aircraft is a Boeing 737-400. It's a land plane powered by two turbofan engines. Figure 4.1 is for optimum altitude. There's an example typically on every graph in the cap. Here let's find the optimum altitude given a cruise mass of 54,000 kilograms, long range cruise or 0.74 Mach. Going in the bottom of the table at 54,000 kilograms, go up to the line which says 0.74 Mach, which is the second one, which is higher up. Then go horizontally left to read a value of 34,600 feet. Figure 4.2 is short distance cruise altitude. For this you go in with a trip distance, vertically up, horizontally right, trade a bit from the reference line, and then go horizontally right again to read the pressure altitude. Let's look at an example for a trip distance of 177 nautical miles. Find this on the left, go vertically up to ISA plus 20 line, go horizontally right to the reference line, then trade down the guidelines to 52,000 kilograms. That'll be a curved line. Then go horizontally right to read a short distance cruise altitude of 28,000 feet. Figures 4.31 A to C are simplified flight planning trip distances. The bottom of the graph has got trip distance, and you go up on this and trade for the headwind or a tailwind. Then you continue upwards to the relevant altitude and then go horizontally right to the reference line and then trade for along the guidelines for the landing weight using particular flight levels in the question. Then go horizontally right to read the fuel required. Now, when we were back coming off from the wind vertically up and selecting the pressure altitude lines, if you were to keep going vertically up, you'd go to pressure altitude again, choose the one for the question, and then go horizontally left to the reference line and trade for ISA deviation. Referring to cap figures 4.3.2 Alpha to Charlie, find the trip time and fuel required for a twin-jet aeroplane with a landing mass of 50,000 kilograms, 0.74 Mach, sector distance of 2,000 nautical ground miles with a 50 knot headwind, ISA, cruising altitude 21,000 feet. Using the figures, you should find 17,000 kilograms, 5 hours and 12 minutes. Referring to figure 4.3.3 A to C, find the trip time and fuel required for the twin-jet aeroplane, giving a landed mass of 40,000 kilograms, 0.78 Mach, a sector distance of 350 nautical ground miles with a 50 knot headwind, ISA minus 10 at a cruising altitude of 29,000 feet. You should find 2,650 kilograms, 1 hour, 6 minutes. Referring to cap 697, 300 knots indicated cruise, which is figure 4.3.4, find the trip time and fuel required for the twin-jet aeroplane, giving a landing mass of 55,000 kilograms, 300 knots indicated airspeed, sector distance 300 nautical ground miles, 100 knot headwind, ISA plus 10 at a cruising altitude of 20,000 feet. You should find 3,400 kilograms, 1 hour 9 minutes. Using figure 4.3.5 for the stepped climb cruise, for a flight of 3,500 ground nautical miles, the following apply. Tailwind 50 knots, temperature ISA plus 10, brake release mass 65,000 kilograms. The trip fuel and trip time should be 18,200 kilograms and 7 hours 20 minutes. Alternate planning is on figure 4.3.6. The distance to the alternate is 300 ground nautical miles, and the following apply. Tailwind component 50 knots, temperature ISA plus 10, landing weight 65,000 kilograms. The trip fuel and trip time should be 2,500 kilograms and 47.5 minutes. For holding fuel planning in figure 4.4, for a weight of 50,000 kilograms at a cruise altitude of 35,000 feet, what's the fuel required for holding for 24 minutes in a normal racetrack hold? You should find 856 kilograms. For holding fuel planning using figure 4.4 in straight and level flight, for a weight of 56,000 kilograms at a cruise altitude of 20,000 feet, what's the fuel required for holding for 36 minutes? This is 1,379.4 kilograms. En route climb is in figure 4.5.1. For a pressure altitude of 28,000 feet, ISA minus 10, and a brake release weight of 58,000 kilograms, what's the time, fuel, nautical air miles and TAS required? You should find 13, 1,150, 63 and 354. Referring to figure 4.5.1 for the en route climb, for a pressure altitude of 24,000 feet, outside air temperature minus 23 and a brake release weight of 60,000 kilograms, what's the time, fuel, NAM and true airspeed required? Well, you might need to calculate ISA deviation here to land on the correct tables, but after doing that you should find 11, 1,100, 54 and 353. For a pressure altitude of 30,000 feet, outside air temperature minus 55 and a brake release weight of 62,000 kilograms, what's the time, fuel, nautical air miles and TAS required? Again, you might need to calculate for ISA and use the correct table, but after that you should find 16, 1,350, 83 and 364. Refer to Flight Planning Manual figure 4.5.3.1. Long range cruise at 27,000 feet, temperature ISA. For a sector A to B, the ground distance is 300 nautical miles. The headwind is 50 knots. The weight at the beginning of the first sector is 55,200 kilograms. What's the fuel required for this sector? Well, you calculate the NAM from the table, you seek it out, looking under 55,000 and then the 200 column. And you should find, if you're on the correct page, 3,716 nautical air miles. From this, you first of all convert your nautical ground miles using the headwind and the TAS from the table into nautical air miles. That should give you 339. Subtract this 339 from the 3,716 that you had earlier. This gives you 3,377. You can think of this as an artificial NAM. Look for the nearest value to this in the table and find the corresponding weight, which is 53,200 kilograms. Subtract this from your start weight to get 2,000 kilograms, and this will be your final answer. The method for using figure 4.5.3.1 can be visualized using this table. You begin with a start weight and you calculate your nautical air miles. Subtract from that the sector NAM. This will give you an artificial NAM. You go in the table with this artificial NAM and find the nearest corresponding mass. Subtract that corresponding mass from your start weight and you'll get the fuel required, and then apply any corrections if necessary. For example, refer to figure 4.5.3.3. It's Mach 0.78, cruising at 31,000 feet. The temperature is ISA. For sector AB, the ground distance is 850 nautical miles. The tailwind is 60 knots. The weight at the beginning of the first sector is 51,600 kilograms. What's the fuel required for the sector? Well, the TAS from the table is 458 knots. Using this TAS and the nautical ground miles and the tailwind to get the ground speed, you should be able to calculate a nautical air miles of 752. Subtract this from the value which is sitting in the table under 51,600 kilograms, your first sector weight, and that should be 3,114. So subtract 752 from that to get 2,362. This is your artificial NAM. Go back into the table, which is with this 2362 value, and look for the corresponding weight. This should be 47,300 kilograms. Subtract that from your start weight, which is 51,600 kilograms, to get the weight of fuel required for the sector of 4,300 kilograms. Refer to figure 4.5.3.4. Low level cruise, 300 knots indicated, at 7,000 feet with a temperature plus 10 from ISA. For sector AB, the ground distance is 360 nautical miles. The headwind is 50 knots. The weight at the beginning of the first sector is 51,400 kilograms. What's the fuel required for the sector? Well, the true airspeed from the table needs to be corrected because we're not in ISA conditions. Read the notes on the table. And that becomes 392 knots. Use this 392 knot corrected TAS to calculate NAM with that 50 knot headwind to obtain a sector NAM of 413 nautical air miles. Go in the table with 51,400 kilograms and find a NAM of 2,428. Subtract from this the sector NAM that you've got to obtain 2,015. This is your artificial NAM. Go back into the table with the 2015 and find the corresponding weight, which is the nearest to it, which is 48,500. Subtract this from your initial start weight, 51,400 kilograms, to get 2,900 kilograms. But because the temperature wasn't ISA, it needs to be corrected to give 2,915 kilograms. Refer to figure 4.5.3.4. Low level cruise, 300 knots indicated at 21,000 feet. The temperature is ISA minus 20. For the sector AB, the ground distance is 660 nautical ground miles with a tailwind of 60 knots. The weight at the beginning of the first sector is 59,100 kilograms. What's the fuel required for this sector? Well, since the temperature is not ISA, there needs to be a correction of the TAS, and that becomes from 406, 386. Use this corrected TAS with the tailwind of 60 knots and the ground distance of 660 nautical miles to obtain the sector NAM of 571. Go in the table 59,100 kilograms to find the corresponding NAM. This is 3,768. Subtract the sector NAM from this to get 3,197. This is your artificial NAM. Go back in the table to find the nearest corresponding weight, which is 55,200 kilograms. Subtract this from your start weight of 59,100 kilograms to get 3,900 kilograms. Correct this though, because the temperature was an ISA, to get the fuel required for the sector of 3,861 kilograms. Refer to figure 4.5.4. This is descent planning. A descent is planned at 0.74 Mach, 250 knots indicated, from 35,000 feet to 5,000 feet. How much fuel will be consumed during this descent? You should get 290 minus 140, which is 150 kilograms. Refer to figure 4.5.4 Bravo. A descent is planned at 0.7 Mach, 250 knots indicated, from 33,000 to 10,000 feet. How much fuel will be consumed and how long will the descent take? You should get 275 minus 185, which is 90, and 20 minus 9, which is 11 minutes. Refer to figure 4.6.1, non-normal operation. Nautical ground mile is 800 with 100 knot tailwind. The pressure altitude is 26,000 feet. The outside air temperature is minus 17 degrees. The landing weight is 45,000 kilograms. How much fuel will be required and how long will the trip time take? You should find 6,450 kilograms, 1 hour 57 minutes. Refer to figure 4.7.1 alpha, critical fuel reserve. The nautical ground miles is 600 with a 50 knot headwind. The weight at the critical point is 50,000 kilograms. How much fuel will be required? You should find 6,050 kilograms. Refer to figure 4.7.1 A to B, critical fuel reserve. The nautical ground miles is 800 with a 50 knot tailwind. The weight at the critical point is 50,000 kilograms. The temperature is ISA in icing conditions. How much fuel will be required? Well, you should find 6,000 kilograms uncorrected. Using graph 1, this becomes 7,200 kilograms, 6,300 kilograms, and 7,434 kilograms, corrected graph 2. The final answer should be 7,434 kilograms. Refer to figure 4.7.3. In-flight diversion, long-range cruise, one engine inoperative. Nautical ground miles is 800. The headwind is 100 knots at 26,000 feet. The weight at the point of diversion is 60,000 kilograms and the temperature is ISA minus 10. What is the fuel required in diversion time? You should find 7,900 kilograms and 3 hours 15 minutes. Refer to medium range jet figure 4.7.3. Given a diversion distance of 650 nautical miles, the diversion pressure altitude is 16,000 feet, the mass at the point of diversion 57,000 kilograms, headwind component 20 knots, temperature ISA plus 15. Find the diversion fuel required and the time. You should find 4,800 kilograms and 2 hours 3 minutes. Refer to figure 4.8.1, fuel tankering, long range cruise. The trip distance is 1,500 nautical air miles at 35,000 feet at 45,000 kilograms. You should find 13.8%. Refer to figure 4.8.2, fuel price differential. The surplus fuel burn-off is 14%, and the fuel price at departure is at 125 cents per gallon. What is the break-even price? You should find 144 cents.